Greetings, everybody. Welcome and thank you for attending my IEEE Sensors 2020 talk about our optical fiber tip micro anemometer. I am Jeremiah Williams, a recent graduate of the Air Force Institute of Technology, and I was able to conduct this research with the help of my advisor, Dr. Hengky Chandrahalim, as well as Dr. Joe Suelzer and Dr. Nick Usechak from the Air Force Research Laboratory. Now let's dive right in. Here is an outline of the presentation I'm going to be giving today. We're going to briefly talk about the motivation for our research into this device, the operating principle, the design of the device itself, our fabrication procedure, the experiment we performed, the results of that experiment, and some potential future work to improve this research going forward. So why did we conduct this research? Well, in general, we want to further miniaturize sensors to lower the size, weight, and power requirements of sensitive systems like satellites or drones. And we also wanted to explore the 3D freedom afforded by this truly amazing two-photon polymerization microfabrication technique, which I'll be discussing later. And some specific applications include smart wings for more efficient aircraft that adapt to their flow environment, and high-fidelity wind tunnels that use whole fields of sensors to get a greater picture of the flow environment. The device operates as a rotor moving around a stator and passing over the core of an optical fiber. Light propagated down the core of the optical fiber reflects off of the rotor blades and back down the fiber when the blades pass over the core. The frequency of these reflection events is determined by the rotational velocity of the rotor. The geometry of the rotor blades, seen here in cross-section, drives this rotation with an angled top surface. The dynamic pressure of flow instant on the blades creates both an axial and lateral reaction, which causes the rotation. This dynamic pressure is determined by the velocity of the flow incident on the device, which in turn depends on the volumetric flow rate and nozzle geometry used to introduce the flow. This driving force is opposed by drag on the rotor blades and friction between the rotor and the stator at the post and the base of the device. We performed some initial analysis with computational fluid dynamics to confirm the operating principle of the device. This indicates that the rotor blade geometry should work as intended and create this resultant force to drive the rotor around the stator. It did also highlight some of the problems that we ran into while operating the device, such as the turbulence at the fiber face and the different reactions experienced by a blade that is over the fiber versus the blades that are not over the fiber. So to get into the design of the device in a little more detail, we have a 3D rendering here of the finished device. Some things to point out are the overall dimensions. You've got the rotor diameter, the stator height, and this 2-micron clearance that we used between the rotor and the stator. Then you've got some developer holes that allow the chemical to get into these tight spaces during fabrication. You've got the curved top portion of the blade, the flat mirror portion of the blade, an adhesion pad to help it adhere to the optical fiber face, and some friction reducing features that are just little hemispheres fabricated on the stator face to reduce friction. So the device couldn't be fabricated as is directly. We needed to utilize a variety of support structures to create the final device. Each of the blades was supported by a larger structure that connected to the blade with an array of 1-micron diameter pillars. 3 of these same pillars also connected the rotor to the stator, so it wasn't just floating in midair during fabrication. Then we used a brick to just mask the core of the optical fiber for when we deposit a reflective coating onto the mirrors of the blades. This kept the fiber face clear, allowing for transmission back down, while also creating the mirrors on the blades. Now, we fabricated our device using two-photon polymerization. This is an additive manufacturing technique, similar to stereolithography 3D printing, in which a photoactive resin is selectively polymerized or solidified with a high-energy laser. Traditionally, this is done with UV light, but the same polymerization energy can be achieved with 2 photons at a higher wavelength. The volume within a laser beam that has sufficient energy for 2-photon polymerization is significantly smaller than the volume capable of single-photon polymerization. Thus, a much smaller voxel, or 3D pixel, can be used to build structures within the resin when using 2-photon polymerization. This technique has already been demonstrated to create some really amazing devices on optical fiber tips, some examples of which are included here. Specifically, we mounted our fiber into a side-loading fiber chuck and loaded it into our two-photon polymerization system, the Nanoscribe Photonic Professional GT. This mounting process took about 20 minutes. Writing the device took about 10 minutes. You can see some of the layers as it was built up from the face of the fiber. You can see our voxel size there, that is in microns. After the device was written, the fiber was immersed into propylene glycol methyl ether acetate, or SU8 developer, for 20 minutes, and then cleaned off with isopropyl alcohol for 10 minutes. The support structures are removed with a semiconductor analysis probe underneath a microscope and discarded. The device is then freed with a slightly larger probe such that the rotor rotates freely. Then the device is transferred into a magnetron sputtering system for the gold reflective film deposition. The fiber is oriented such that the fiber face is orthogonal to the sputtering target, allowing the deposition to reach the mirrors on the bottoms of the blades. Then the masking brick is removed and the device is ready for operation. The key to testing the device lies in the optical circulator. This is a pretty amazing off-the-shelf optical component where light can transmit freely from port 1 to port 2 and port 2 to port 3, but suffers high losses in the opposite direction. Thus, you essentially have a one-way optical component where the reflection off of anything connected to port 2 can be isolated and analyzed. We connected a laser at 1550 nanometers to port 1. This is the operating wavelength of the fiber and the optical circulator. Our device to port 2, and a photoreceiver to port 3 to analyze the reflection off of the device. The device was mounted into a mirror mount adapted to the fiber chuck such that we could precisely control the orientation of the fiber in respect to the flow. The flow was directed onto the device with a nozzle created from a 1/8 inch compression fitting connected through a flow meter to our compressed nitrogen. Thus we could control the volumetric flow rate and velocity of the nitrogen onto the device. To confirm operation of the device, we did analyze it underneath a microscopic high-speed camera. Unfortunately, the high-speed camera setup was geographically separated from our other experiment, and so the nitrogen applied in this footage was with a handheld nitrogen gun and not particularly consistent or orthogonal to the device. We hope to, in future work, combine both setups such that we can analyze the rotation underneath a high-speed camera in a stable flow environment. The reflection output of the device, as read by the photodetector, is somewhat less than ideal, but still serves to prove the concept of the device. The photodetector outputs a voltage that is read on an oscilloscope. This figure shows the readings from two measurements at different flow rates. The segments included here have been normalized and offset to appear on the same plot. To analyze the reflection signal, a low-pass filter is applied to smooth out random noise, and the local peaks are counted as an estimate of the number of reflection events. There are inevitably some false positives and missed peaks, but the same procedure is applied to each measurement for consistent analysis. We had hoped for a repeated frequency to dominate this signal, but the device produces reflections at choppy, seemingly random intervals instead. We believe this is caused by inconsistent rotation due to the turbulence around the fiber face and the subsequent backflow onto the bottoms of the rotor blades. Sticking friction between the rotor and the stator also likely contributes to this inconsistency. We hope to improve this situation with improvements to the device design in future work. Despite the lack of periodicity, the number of events over a given time period is still dependent on the volumetric flow rate and the incident flow. Thus, the number of reflection events counted over a 1/2 second interval is taken as the output of the device. The device was tested over two different flow ranges, a coarse range from 9.35 to 24.25 liters per minute, and a fine range from 10.97 to 11.79 liters per minute. The larger range test showed a nonlinear response, and further investigation is necessary to determine if this was caused by the actual rotation of the device reaching a limit and slowing down, or some kind of limit in the peak counting algorithm unable to keep up with the frequency of events. Despite this, the device successfully demonstrated operation at high flows and velocities, proving it can survive in these regimes. Over the smaller range, the response is linear, making this a preferred operating region for the device as it is currently. Vertical error bars in these plots represent one standard deviation of repeated measurements, and horizontal error bars represent the repeatability of the flow meter. While we successfully designed, fabricated, and tested this device, there's still plenty of room for improvement and future work. One of our first pushes is to find a lubricant or alternative bearing design to improve the rotational stability. This figure on the right showcases the results of an initial investigation with a common, off-the-shelf silicone lubricant applied to the device. While the reflection events are much more consistent, lengthy, and noticeable, the results were not consistent over time with repeated measurements, so further investigation and an alternative lubricant might be needed. We also hope to examine flow parallel to the fiber face, which may reduce the backflow seen with perpendicular flow. We'd also like to investigate the device in sensing liquids, devise a protective housing for the sensor, and demonstrate an array of devices for flow field mapping. This concludes my presentation. Thank you all for sticking with me. I'd like to give a special acknowledgement to the project sponsor at AFOSR, the AFRL Materials Directorate staff who helped with the nanoscribe, and the AFIC cleanroom staff who helped with our thin film sputtering and the space to do these experiments. Everybody stay safe and have a great day. Thank you again.